Good morning and most welcome to Heidegger 1391. We are slowly approaching the 1400s, and today we will open up a new chapter, a new direction in physics, started with, amongst others, the scientist David Deutsch. And later expounded by Chiara Marletto in her book The Science of Can and Can't. A physicist's journey through the land of contrafactuals. Since this is the first start of this new theory, I will take it in sections. Let me first try to paint out what is a counterfactual. And then I will read some of the book. I will make a course summary and have some questions. And once more go through the example I mentioned here in the beginning. I did actually fall asleep with the book yesterday, but that doesn't mean it was not interesting. One of the examples of contrafactuals that Chiara Marletto brings up is the contrast between the physics of Galilei, and the then dominant physics of Aristotle. Chiara paints up a vision where it becomes obvious that for Galilei to make his revolution, the counter to Galileo had to be present. his formulation for his novel idea is cast in the mold of Aristotelian formalism. Galileo is using no's and nots to show what his ideas are. I'll give you one example. Objects of different weights do not fall at different speed. That is a contrafactual proposition. So, although completely novel in all aspects, the Galilean discovery is germinated in Aristotelian knowledge. The formalism of Aristotle needs to be present. It is the material, so to speak. As in the previous lecture, this can be compared to the British Maltesian creativist philosopher Edward de Bono, who shows in his books that a strict system is the growth material of lateral thinking or disjunct thinking. One way of thinking of it is as a nutritious substrate. And once it been used, it disappears. Chiara means it is still partaking. The development of knowledge is a crucial part of what knowing is now. To help in a little bit more, I can here also add Terence Deacon, who points to the absolute necessity and participating role of absence. The absence in Terence Deacon's philosophy can be compared to the absent contrafactual of Aristotle in the Galilean worldview. It's constitutive, to use Deacon's own words, of present truth. In the same way as the air or emptiness in a wheel between the spokes are constitutive of what makes up a wheel. Without that absence, that negation of matter, the wheel would not have stability, strength, and balance. All modern wheels have more absence than matter. constructions of great size in modern architecture are also suffused by contradiction or absence. They are extremely light, in contrast to buildings of the past. That absence is also reminiscent of the Derridian absence. That is constituent of the text, the air between the spokes of the letter N makes it an N. I will read the Galileo example in Chiara's own writing, chapter 2, page 48, the last paragraph. Why is testability of predictions so central to the progress of physics and science in general? The reason is that it provides a particularly efficient way to find mistakes in the explanations and correct them. I want to open a digression to illustrate how predictions, explanation, and testing are all intertwined within the method that allows science to make tentative progress. To this end, let me stir the cloudy water in the pond of history and bring up the spirit of the thinker who pioneered the scientific method as we know it. Galileo Galilei. Galileo's experiments to test his predictions are striking for their beauty and simplicity. He intended to test his theory's prediction about the motion of systems against those that Aristotle had proposed in antiquity. Which had been considered the authority ever since. Galileo's predictions were about the motion of a hard, smooth bronze sphere left free to roll inside an inclined, smooth groove. The same speed in particular. This prediction was in sharp conflict with Aristotle's theory. Which predicted that spheres of different masses would roll down with different speeds. On the face of it, Aristotle's idea seems intuitively true. Which makes Galileo's predictions all the more interesting. Why did Galileo make that prediction despite its going against common sense? The answer lies once more in the underlying explanation. This explanation is based on a thought experiment that Galileo invented. A thought experiment is an elegant intellectual device. It does not have to take place in reality. It just takes place in the mind. Enabling us to reach some conclusions. The thought experiment in question allowed Galileo to predict that spheres of different masses should roll down the groove, undergoing the same motion. With the same speed. However, the experiment itself applies to a simple case the motion of systems dropped from a high place and left free to fall. Aristotle's theory, as I said, was that the speed of the falling system would be greater the larger its mass. For example, Aristotle would say that a smaller bronze sphere would go down slower than a larger one, dropped from the same height. My comment, this is the formalism, the material, so to speak. To disprove this theory, Galileo first assumed Aristotle's idea was true. Important, and let me repeat it. To disprove this theory, Galileo first assumed Aristotle's idea was true. Then he showed that by following the logical implications of that idea, one reaches a conclusion that is in contradiction with that very assumption. As a general principle, whenever one supposes that something is true and then reaches a contradiction, one can conclude that the assumption is false. Reach the contradiction, Galileo reasoned like this: if one joins a smaller sphere to a larger sphere via a string and then drops them both from a height, what happens, according to Aristotle, is that the smaller sphere has a smaller velocity. In this thought experiment, the smaller sphere should lag behind. If the two spheres can fall down for a long enough stretch, the smaller sphere would slow down the larger sphere by pulling on the strings. So the combined system made of two spheres would go down at a speed that is slower than that of the larger sphere by itself. But here is the glitch. This contradicts Aristotle's idea that systems with larger masses should have larger velocities. My comment, here you can see Aristotle is participating, but in a formal way. After all, the system made of the two connected spheres has a larger mass than the larger sphere by itself. If Aristotle's idea were true, it should be faster not slower as we concluded. Therefore, by this thought experiment, Galileo was led to conclude that Aristotle's idea was false. And that spheres of different masses should undergo the same motion when falling freely. He then conjectured with another leap of creativity that they should display the same behavior when sliding down the groove. So you see here my comment. We haven't even in real life tested anything, but using the contrafactuality, a discovery is already made. Galileo went on to test the latter prediction against Aristotle's ideas by observation. Here is where testability of the prediction is important. He first observed what happens to the sphere when the groove is not inclined. He noticed that when the sphere is given an initial gentle push, and then it is left free to move along it. It undergoes a motion that he called in Italian equabile, which means uniform. In his words, that means that the spheres traverses equal space intervals in equal time intervals. In modern physics, we would say that its velocity is constant. Galileo then observed that when the groove is inclined, the sphere undergoes a different motion. In equal time intervals, it moves by increasing space intervals. Its motion is accelerated. Then Galileo tried the same experiment with different masses and observed that the behavior was the same for all of them. All the masses were undergoing the same motion with the same speed and acceleration, just like he had predicted. So Galileo's experiments refuted Aristotle's theory. which as a consequence was forever dismissed. The very last sentence here is important. So Galileo's experiments refuted Aristotle's theory, which as a consequence was forever dismissed. It after that disappeared from knowledge. We are, so to speak, left with the end product. Chiara is pointing to that Aristotle still is present. Without the formalism, the material of Aristotle, Galileo's discovery would never be possible. That is from our perspective today very hard to, so to speak, etymologically understand. We have just out of nowhere, everywhere, Galileo's idea of motion. So the contrafactual disappears from vision. So we are left only with the truth side of the page, whereas the other side gets covered up by us looking at the truth. Galileo demolished at least 1500 years of thinking that size, mass, and velocity are connected. Galileo's new worldview was the fertile soil for later developments during the coming centuries. Let me just try to show the rather simple example depicted in the book. First, you have one smaller object, and supposedly it moves slower to the ground than a bigger object. To the smaller object, you attach with a string a bigger object. That object should be slowed down by the smaller object, and thereby the thinking of Aristotle gets contradicted already before the experiment. This is one example of the power of a cannot or can't. It cannot move slower because then it contradicts what Aristotle laid forward all those years ago. This is a first little example in the very beginning of the book to give you a little taste of contrafactuals before we go deeper into what a can't is. Maybe a comment? Do you want to be by the...
Hello. I think sometimes it can be instructive to compare to another theories, like the chaos theory. It can help to promote lateral thinking, like in the famous lateral thinking by Edward de Bono. So in chaos theory you have the famous butterfly effect. And let's say the theory is that if a butterfly moves its wings, flaps its wings, it can cause a storm. And it doesn't, so it's a scale independency. So say a butterfly, an elephant, they moving the bodies has the same effect, to simplify the idea of scale independency in chaos theory. So let me put it differently. I can, let's say here, to make the illustration easy to follow with the Aristotle's example and Galileo's example. So let me put, let's say, a butterfly here, and let's say an elephant. Can you check hands that the viewer sees this in the box? So you have good. So you have a butterfly here, and it's moving its wings a little bit, and the elephant is moving its tail a little bit. And in both cases, you have a storm. The storm is no less smaller in this case and this case. So you have, let's say, the butterfly causes a storm. The butterfly happens for some reason or another be on a mountain. Let's say it's on a mountain, an elephant is also on a mountain. Let's say in India or somewhere. Then down the mountain, you then have a huge storm. And so how would you, Hans, is the idea similar to Galileo's discovery, or in what way is it dissimilar? So I hand it back to you. Hopefully we will get some lateral thinking.
Why, thank you, Kalle. That was definitely lateral, and I do like the initiative. Yes, spontaneously I would say yes, because the regular idea, the Aristotelian idea of size, mass, is contradicted by chaos theory, and so is the Newtonian concept that bigger mass, bigger size means bigger influence. And another spontaneous thing I can say in this connection is that without the formalism of the Newtonian matter, the contradiction of Konrad Lorenz and Mandelbrot would not be possible. They use the old format, which is size equals influence, and they see a contrafactual in the butterfly, which weighs a couple of grams, and compare to an elephant that weighs tons. In the weather system, Lorenz showed that a very, very, very minute effect can have tremendous impact. And here you see the contrafactual. You also see that it is the material of chaos theory by itself, without the formalism of the Newtonian. Chaos theory could not have developed. It needs a contrafactual. That contrafactual happened that very important afternoon in the weather station where the butterfly effect was discovered. So to conclude, as we usually assume that discoveries sort of get picked out of nowhere and that they can come out of isolation, is questioned by Chiara Marletto, but also shown to be a very valuable tool for thinking and doing things. But I will continue to that the next part. We can put a little pause. So we continue. So the absence is constitutive of what's being made. Here in Gothenburg, in the amusement park of Liseberg, it seems, a geodesic dome is being constructed. This one is a contrafactual to the massive buildings of the past. Very light, but extremely strong. So it's taking as its constituents absence, but also see that the inventor of the geodesic dome, Buckminster Fuller, also made his discoveries in contrafactual terms, in theory and in construction calculations. The building next to it in red brick is of another theory, but also of another materiality. And that is one trait that you will see more and more as lectures progress. Somehow the line or the border between what is thought, the theory, or the thinking gets dissolved, what is made, the materiality. Such is the strength of the counterfactual. I continue on page 51. This example illustrates how the testability of predictions in physics and in science in general is central for the possibility of error correction. And therefore, for the progress of science as a whole. explanations whose predictions are found wrong in an experiment automatically become problematic. And they are usually dismissed in favor of alternative explanations. My comment here, do note that the very word alternative need to have its counterpart in the original to be an alternative. Excuse me. As mentioned in the first chapter, Galileo's and Newton's explanations and the resulting predictions have an important trait in common. Their approach to explaining physical reality is centered on what is usually called a law of motion. A law of motion, or a dynamical law, is a description of where a system goes. Given that its motion starts at a certain point in space and time. Think of a sequence of snapshots. Each of which represents the state of that system at different times. The law of motion provides the rule for how the snapshots are ordered. In particular, there will be an initial and final snapshot representing the starting and ending states of the motion. Which in physics jargon are called initial conditions and final conditions. For instance, in the case of a ball fired by a cannon, the initial snapshot contains the ball sitting inside the cannon, about to be fired. The final snapshot represents it when it lands on the ground. Typically, any snapshot along the sequence is explained in terms of its predecessor. Ultimately, in terms of the initial snapshot. Now, all sequences of snapshots described by known laws of motion have a particular property. Each snapshot has only one predecessor and one successor in the sequence. This property is something physicists call reversibility of dynamical laws. Once you have gone all the way down the sequence of snapshots, you can go back without any uncertainty. Because each snapshot has only one predecessor. Unlike in a garden or a labyrinth, with forking paths, therefore, no bifurcations occur along the line. There is no ambiguity in how to go back and forth. This is very, very pertinent. No bifurcations occur along the line. There is no ambiguity in how to go back and forth. The explanation by laws of motion is the most traditional in physics. It was first introduced by Galileo. Then it became established with Newton's laws. Today, the two most fundamental physical theories general relativity and quantum theory are expressed via laws of motion too. And so are all other theories that physicists generally consider fundamental, like those governing electromagnetic fields and elementary particles. The long-term success of the approach by laws of motion is remarkable. Its predictions are extremely powerful. Suppose, for instance, you were a general about to attack a city protected by robust walls. Which you want to batter down. Newton's laws tell you exactly how to tilt the cannon in order to maximize the impact of its projectiles. By predicting their motion in every detail. For example, they tell you that there are only two possible paths available to the same point of impact for a cannonball with any particular initial speed. In both cases, the ball describes a parabola in the air, but with different maximum heights. Depending on the initial condition. The angle in which the cannon is tilted initially. When the cannon is tilted at a high angle, the ball flies high and falls down beyond the walls. If the cannon is tilted at a lower angle, the ball flies lower. And it can, if the angle is right, strike the protective wall. In both cases, the description of what is going on is encapsulated in the sequence of places the ball traverses as time goes by. This set of places is the ball's trajectory, its path, which is dictated by the laws of motion. Newton's, no, I'll just read out. Excuse me. Newton's law in this case in this approach, the explanation for why the ball hits the target at the end is given in terms of the places the ball goes through. Ultimately, as I said, in terms of its initial position and velocity. The initial conditions of the system's motion. Since the dynamical law approach is so powerful, it is natural to wonder whether it could be extended to explain everything that happens in our universe. Including the whole universe in itself. In other words, would a physical theory of the initial conditions of the universe and of its laws of motion provide a satisfactory explanation for everything in it? The answer, as you are about to discover is new. I shall point out that explanations in the form of laws of motion and initial conditions are excellent for special purpose. That is, to make predictions about what happens on a subpart of the universe. Like cannonballs, marbles, and planets. But they cannot explain everything in the physical reality. In fact, when regarded as an explanation of everything, they have serious problems. Problems are fruitful things in physics, as they are in life. They hold the promise of improvement when they are addressed properly. These problems are the very reason why we have to venture on our journey in the land of contrafactuals. As I said, the dynamical law type of explanation looks like a sequence of snapshots. It has an initial and a final snapshot, and there are all the snapshots in between, whose order is set by the laws of motion. The explanation for something happening on an intermediate snapshot for example, the cannonball suspended in the air at the highest point of its trajectory. Is in terms of what happens in the snapshots before and after that particular snapshot. I put a pause and let me make some explanation here. So, to help ease the understanding that is coming, the more complicated business, let me lead you through the trajectory of the cannonball, because it is in itself a contradictory invention, set at the background of the Aristotelian stillness of movement. We now invent that each phase, each dividing line, is in itself a section of space and time that gives velocity. Together with initial conditions from the brim of the cannon, the amount of gunpowder, the trajectory of the cannonball can be calculated so for it to reach the desired, for instance, in this case, a tower. This is contradicting Aristotelian stillness. Just testing here. And that will introduce movement velocity. We have gone through this earlier, many episodes ago. It is the best explanation of what happens later, 1689 and other decisive years. And something gets built up as contradicting something else. and it's extremely practical to a certain level, as Chiara herself already have pointed out. We do not know the reason for it. As you who have followed the series, you probably know the problems that comes when applying a contrafactual statement like this one, an invention, and you understanding, to reality as a whole. My own thinking here is that if we remember what gets contradicted here, the Greek stillness, and that we can bring that understanding of what was previous and what is part of the current explanation into that explanation, its absence, we will be on a safer ground, and we will not be tempted to put it into the whole of the universe, for instance. We become grounded with contrafactuals in time, because it has etymological traits, so to speak, and also in space, because we acknowledge also the absence. Thereby we have loads more information. Remember Galileo and how we meet Galileo today, as if his ideas just fell from the sky. They become ungrounded in the Geschichte of knowledge. And I would say they become less foundational, stable, less exact, because it's a lack of exactness to transfer this to the whole of universe. We lost its why, its being. Maybe Kalle, a short comment.
Thank you. Okay. So I would like to, as you alluded to Zeno's paradox, and we can take it in again, like the Zeno's paradox. We can think about the hair and the turtle. So we have the, let's say, instead of this we have the hair. Does it appear? Okay, hair, and then let's say the turtle here. And then we can, should we place it, where should we place the turtle? I don't even remember if they even have the same.
It has an advantage, yes.
Yes, indeed. In Zeno's paradox, turtle does have an advantage. And for Zenon, then turtle wins, so to say, because for every movement. So first, let's say hair have to cover 1 meter, and then half of the half meter, and then half of that, and half of that. So he never reaches the turtle.
No.
And the resolution is from quantum physics. It would be the observer. We can place the observer, say, like here. An observer, of course, sees that this is absurd. The observer sees that is the hair who wins. And we have, let's say, how do you say that? We have also the light from Mikis-Morley experiment for 1987, and in this say we have often said that everything is relative. Yes, it's relative, but light is not relative. So at the very moment that this observer sees this, you have how would we say that? Light is not relative, so so the hair and the turtle are one and the same, because the light is also is emanating from the hair to the observer, like in my this homonym I, this I, and the pronoun I and the noun I. So there is no distinction between, let's say, my I and the hair, the eye of the eye of the hair either. So the observer, so to say, creates reality thanks to the very light that binds the observer to this. Although, how do you, so to say, combine quantum physics with the Mikis-Morley experiment? So the observer needs the light. The observer creates reality, and for this reality to happen, you need also light that, so to say, abolishes distances. Do you want to add something, Hans?
Very quickly, and that will have to be that. Yes, very good. Morrison-Morley experiment is a contradictory to this. So this model, they proved, doesn't hold for the whole of the universe. Yes, this is how it is. We will observe the hair catching up the hair and the tortoise. That will actually happen. So we are saved from the contrafactual evidence. So one could say that quantum mechanics makes up another very interesting contrafactual. Thank you very much and have a very pleasant afternoon.
Thank you.